Assalamu alaikum. This is the third video of first chapter. So till now we have discussed that basically in steady state operation we have to maintain the AC power side and we have to maintain the DC power side, and both the AC and DC power side will be maintained if and only if the voltages of the submodule capacitors are balanced. So in that case the power will be balanced. So this condition was discussed in steady state operation of the MMC. Then we did discuss that in half bridge submodule what happens whenever the DC side short circuit faults occur, the converter loses its overall control on the converter, and because of that sir hostel guy sir जी sir, and because of that H bridge submodule topology is this is basically the drawback of H bridge submodule topology, that it loses its control of the converter whenever the stiff DC fault occurs. And at that time when the stiff DC fault occur, you can see that a very high short circuit current flows from the converter, and because of this high current there are chances that the diodes of the half bridge the diodes of the half bridge may burn out until the circuit breaker opens from the AC side to basically discriminate the faulty and healthy and unhealthy portion of the system. So this is now we have discussed. So now let's move on and discuss what are the other uses of converter. Basically these conventional converters are basically can be used as a source of supplying reactive power and source of consuming reactive power. So reactive power compensator, basically in AC system we need, in order to maintain the voltage profile, we need a certain amount of reactive power, and that reactive power can be supplied using static compensator with cascaded H bridge full bridges. So we can use them in order to generate the reactive power. They can inject the reactive power into the system in order to improve the voltage profile of the system, and they can consume the reactive power whenever there is an excess of reactive power. So reactive power compensation is basically required for better utilization of grid to provide reactive power in high fluctuating loads. Static compensator, we call them statcoms, are used for that purpose. So these are basically voltage source converters that are connected with grid and whose sole purpose is to generate and absorb reactive power, right? So in the early times, two level converters or neutral point clamp converters were basically used to handle greater amount of power in order to consume reactive power and to generate reactive power. So this diagram you can see that what is happening from the grid, we are taking the active power, and using statcom we are basically generating reactive power, and this is the load. So both active and reactive power is basically supplied to the load. So this is an application of statcom. Statcom is basically static compensator. So yes, this is Y connected full bridge converter for providing reactive power, and we have used a reactor here at the terminal, AC side terminal, to limit the harmonic current. Now converter can generate reactive power and it can absorb reactive power depending upon the value of this angle. Similarly, using statcom, wire connected statcom, second order harmonic will be generated as in case of half bridge that may give rise to the ripple voltage. So this is basically the equation which shows that the reactive power is consumed and generated, and here no DC source is available. Now, according to the literature, it is said that whenever your load is unbalanced, you may use delta connected statcom as well. Okay, this was one of the application of the statcom, static compensator. Now we are moving towards the next topology, that is full bridge submodule topology. So we did see that in half bridge submodule topology, uh, the half bridge topology is unable to it loses its control of the converter whenever a stiff DC fault occur at the DC line. Now we are going to see that what happens whenever we are using the full bridge converter in our system in order to uh, simply used full bridge as an MMC. Now it was the drawback of the half bridge submodule topology that it loses its control whenever the stiff DC fault occur at the DC side. Now that drawback of fault current handling is basically overcome by the full bridge submodule. Since full bridge submodule can provide bipolar voltage, so the converter can handle both AC and DC side currents even if DC short circuit occurs. This is basically the beauty of the full bridge MMC. So in so this is the beauty of full bridge MMC, uh, that it can operate for modulation index greater than 1. That means that the instantaneous output AC side voltage can exceed the applied DC side voltage. So because of this excellent feature, we can say that full bridge MMC can basically handle the fault current, because here we can see that the voltage is exceeding the DC side voltage. The instantaneous AC voltage is exceeding the DC side applied voltage. So we can assume that the fault current will be low in that case, and converter is able to control that converter is able to control the operation of converter if stiff DC fault is occurring at the DC side. And we know that the main difference between half bridge and full bridge is the region where they can operate. Now, for modulation index greater than 1, the instantaneous peak voltage can be greater than the supplied voltage. This is, as I earlier discussed, that this is the beauty of the full bridge submodule topology, that the instantaneous voltage can also be greater than the half of the DC pole to pole voltage. Yes, another attractive feature of full bridge MMC is that DC polarity reversal may occur. You can see here that in this particular diagram, this is basically showing that you can basically get half of the instantaneous capacitor voltage. Why? Because unipolar voltage is available in half bridge submodule topology. But in case of full bridge submodule topology, you are basically getting plus VC, 0 and minus VC. So overall voltage becomes VC. Overall voltage becomes VC. So here you can see that the operating range of half bridge submodule is unipolar, but in case of full bridge submodule you can see that its operating range is basically minus twice of VC, 0 and twice of VC. So it can provide you negative voltage as well. This feature is only valid when the submodule capacitor voltages are balanced. Okay. Increase in the modulation index above 1 can certainly basically decrease the energy variation of the submodule capacitor. Yes, if you are increasing the modulation index above 1, that means energy variation of the submodule capacitor will definitely decrease, and that's why in full bridge submodule you can use the smaller size of the capacitor. So in terms of cost, full bridge submodule, no doubt we are using double the number of semiconductor devices, but in terms of cost, if we compare full bridge submodule with half bridge submodule, the size of capacitor in full bridge submodule is less as compared to half bridge submodule. So in terms of semiconductor devices, full bridge seems less attractive due to high number of switches, and this is also the drawback of full bridge submodule, that our losses are increased and even they are double as compared to half bridge submodule, but the switching frequency is half as compared to uh, half bridge submodule. So till now we have discussed that what were the basically drawbacks of half bridge submodule, that it loses its control whenever a stiff DC fault occur at the DC side, and that particular problem has overcome by full bridge submodule, and due to its beauty of working of modulation index greater than 1, because of that it can provide you negative voltage, and that negative voltage can increase its operating range, and because of that the current reduces, and if the current is reducing as compared to half bridge, so we are saying that the full bridge submodule, the full bridge converter, if you are using full bridge converter topology in modular multi-level converter, that can basically control the fault current as compared to half bridge submodule topology. And moreover, the losses are in full bridge submodule topology, the losses are high, but your switching frequency reduces to half as compared to half bridge submodule topology, and there is no energy variation in the capacitor voltage because your modulation index is greater than 1. And if this is happening, then you can use a capacitor whose energy is low. That means you are basically saving your cost, saving your initial cost, but again there is a compromise between half bridge and full bridge submodule topology. So this is all about half bridge topology and full bridge topology that is used in modular multi-level converter. Now we are going to discuss, okay, what happens if we are using a conventional two-level converter with topology or with full bridge topology, what happens? So the next upcoming topology is basically alternate arm converter. Now this topology is basically the mixture of conventional converter and modular multi-level converter. You can see here in the upper arm, high voltage valves are connected in series in order to distribute the voltage stress between these switches, and in the lower arm you can see full bridge cells are connected in series. So this alternate arm converter topology is basically, or it can be used as an inverter. Now you can see, using the full bridge submodule topology, we can basically control the DC side fault current. If the steep DC side fault is occurring at the DC side, we can basically control because of this full bridge, and using uh, series connected switches in the upper arm, we can say that our cost has been reduced as compared to full bridge topology. So this alternate arm converter is basically uh, combination of conventional converters and full bridge topology. So it is capable of blocking DC side currents whenever a steep DC side fault occurs, and it is basically, it combines, its arm combines strings of valves connected in series and full bridge topology, and full bridge provides the capability of handling current in whenever a DC side fault occurs, as I said earlier. So its working is very simple. Now for half of the cycle, uh, for half of the cycle, the switch is connected in the upper arm will conduct, and whenever the switch conducts, we can get basically Vd by 2 minus Vs voltage, where Vs is the instantaneous voltage. Similarly, for the next of the half cycle, the lower arm conducts with negative AC EMF, and hence we are getting Vdc by 2 plus Vs, where Vs is the instantaneous voltage. Now you can see here its operation basically resembles to the two level converter, but it is different from that, since we are using since the switches are not in series, but there is a combination of full bridge modular multi-level converter with conventional converter. Since now, according to literature, what it says that it is different from MMC. MMC looks like a multi-level voltage source converter from both AC and DC side of the network, but alternate arm converter seems as a current source, as a current source, since it is constantly injecting half of the AC current into one of the DC pole, and other half of the cycle into other DC pole. So it is acting as a current source, since it is injecting half of the AC current into the DC pole and other half of the current in the next cycle. So it is acting as it seems as a current source converter. So a three phase two level converter produces high frequency. If we are using alternate arm converter with having a three phases, so it basically injects harmonics that are multiples of 6 times the fundamental frequency. So alternate arm converter, there must be a fixed ratio between AC and DC side voltage to balance the power flow. Now in order to balance the power flow, we have to fix this AC and DC side voltage. The ratio between them must be fixed, and this is the average power 1 by 2 VSIS, where VSIS are the instantaneous voltage and instantaneous current, and cos phi is the power factor. And this is the DC side expression, keeping in mind that current injected into the DC pole has half of the cycle of the sinusoid. So it is basically 1 by pi, 0 to pi. We are taking half of the cycle since the current injected into the DC pole is basically for half of the period. So if we compare both of the equations, we are basically getting instantaneous, this equation which shows that the instantaneous voltage is related with the DC side pole to pole voltage with a factor of 2 by pi. Now alternate arm converters can only work in a particular operating area which is known as a sweet spot. Please note one thing here, that alternate arm converters works efficiently or works perfectly in the sweet spot. If you are using alternate arm converter outside this sweet spot, there will be an unbalancing of capacitor voltages and the converter may collapse. So outside this spot there won't be a natural balancing of AC and DC power flow, and it will certainly leads to the uncontrolled drift of submodule capacitor voltages, and our converter may collapse. And the modulation index corresponding to sweet spot area is this 4 by pi, which is, so this is the advantage. Here I want to discuss the advantage of alternate arm converter, that its modulation index is basically greater than the two level converter or H bridge converter, whereas the full bridge converter can operate in any modulation index, as I discussed earlier. So energy fluctuation as compared to half bridge is small in alternate arm converter, hence require smaller value of capacitor and the cost is saved. So now in terms of cost, alternate arm converter basically lies in between half bridge and full bridge submodule topology. So now if I summarize what we have discussed so far, we have discussed three topologies that are used basically in modular multi-level converter: half bridge topology, full bridge topology, and alternate arm converter. So in the past, half bridge topology was basically a success towards the modular based converter, and but its drawback that it loses its control whenever a stiff DC fault occurs. We know it was simple in construction since it has only two switches with a capacitor connected in parallel across them. It has less semiconductor devices. We only need two switches, and but its switching frequency as compared to full bridge is higher. And if we see full bridge topology, so higher number of levels we can get. It has a capability of current controlling during stiff DC fault, but it is complex in structure and it has more semiconductor devices, but its switching frequency is low as compared to half bridge topology. We can also compare half bridge and full bridge in terms of its modulation index, that half bridge can operate in the modulation index between 0 and 1, but full bridge can operate for a modulation index of greater than 1. You can increase modulation index greater than 1, and there is an advantage of doing that the energy pulsation, energy fluctuations are very low, and because of that you can use smaller values of capacitor compared to the half bridge, and you can save the initial cost of the converter. So in case of full bridge, the initial cost of the capacitors will be very low, but in terms of the cost of the semiconductor switches will be doubled as compared to half bridge. So there is a trade-off, but since full bridge can control fault currents, can deal with the fault currents, so we can prefer full bridge topology over half bridge topology. Now in alternate arm converter, we see that the number of levels are moderate, or the number of levels are not more as compared to half bridge. It can operate at a moderate modulation index between half bridge and full bridge, which was 4 by pi, and it has lesser energy fluctuation as compared to half bridge, but as compared to full bridge it will be more. And size of capacitor needed is smaller, since due to low ripple voltage, and moderate semiconductor devices are used compared to half bridge and full bridge. So this was all about the half bridge, the full bridge, and alternate arm converter. And we did discuss in the previous slide that uh, what were the drawbacks of conventional two-level converter, and then we did discuss about the multi-level converter, neutral point clamped, and flying capacitor, and we can compare them uh, with the modular multi-level converter.